who will explain us, will tell us why we should consider WebAssembly in our next front-end project. So, Håkan, can you hear it? Can you? Yeah.
Yeah, sure. So first of all, I just want to thank everyone for coming to this meetup. And the topic for today is about why you should consider WebAssembly in your next front-end project. But before we start here, so this is the agenda here for tonight. So first I'm going to explain you what is WebAssembly. Then we're going to go through, simple hello WASM example. And then I will give you an introduction to Rust, because what we will do is we will build a simple application here using Rust, and then we will compile Rust down to WebAssembly. And then what we will do is we will package this WebAssembly into an NPM package that we will upload to NPM. And then we will just create, a web application so that we can see that we can actually reuse this WebAssembly that we've made. And we're going to also go through some more real-world examples and also what is in the future for WASP and other frameworks that are also using WASP. So I hope this is going to be an interesting presentation here. But before we start, I'm just going to say a couple of words here about me. So my background is I'm actually been working with human-machine interfaces for process automation and robotics. And my educational background is a master's degree in electrical engineering and also a master's degree in behavior science. And I'm also interested in artificial intelligence and Internet of Things. So I've taken some classes at MIT. So I'm a Microsoft MVP in AI, and I'm also quite involved here in the local user group community here in Oslo. So I'm part of Oslo.AI, and I'm also part of the Norwegian.net user group. But to start things off here, we first need to understand what is WebAssembly. So WebAssembly, it started out in 2015. So all the major browsers, they got together and formed a group, a task group. And then 2 years later, they had the WebAssembly was released. And the thing with WebAssembly is that it's actually a W3C standard. So that means that this is implemented by all the major browsers, both in the desktop version, but also in the mobile versions. And this is a real strength with WebAssembly, so that you don't really need to think about it. You can just use it out of the box. So if we try to understand a little bit more what WebAssembly is, so we can compare it with JavaScript. So as you know, JavaScript is a high-level language. It's very flexible and expressive. You don't need to compile, and it has this huge ecosystem that you can make use of. Whereas WebAssembly, or WASM as it's also called, is much more low-level assembly-like language, as we will see a little bit further on here. And it also has a compact binary format, and what it promises us is a near-native performance. So, for example, if you want to do some image or video transformation, or perhaps you're doing some mathematical calculations, or you want to do a game and you want to do some graphic renders, for example, then that's a good example for where WebAssembly can come into play. So as of now, what you're doing is you compile a high-level language down to WebAssembly. So you can use either C or C++ or Rust or Go, and then you can compile these things down to WebAssembly and use them. So one of the reasons why WebAssembly was so quickly developed was because it's based on a previous project called ASM.js. So if you're interested in that, I propose that you look into a little bit of history of that project, because that's quite interesting. So WebAssembly is an intermediate language in the same way as when you program in Java, it compiles down to bytecode, or if you program in C#, it will compile down to MSIL. So with WebAssembly, we have 4 different types. We have 32-bit integers, 64-bit integers, 32-bit floats, and 64-bit floats. So if we want to write here a hello WASM example, as I said here in my previous slide, you saw that we only had float and integers, so we don't really have any strings or characters. So that's why when you write a hello world program in WASM, you actually rather would like to do it as a mathematical calculation. So what we're going to do is we're going to make an add program here. So what we do here is there's a format called WAT, which is WebAssembly text format. And then you can just write your WebAssembly module. So you define a module, you define a function name, you define the input parameters and the output parameters as a result. And then WebAssembly is a stack-based language. You can push and pop on the stack. And then there are some 60 different type of mathematical functions or logical functions that you can use. So for example, in this, we are putting things on the stack, and then we're using the I32 add function to add these two numbers together. And then we can export this as a name. So we name this function as add2, and then we can use it in a calling application. So this is what it actually looks like if you would look into how this code looks like. So it's very similar to assembly code. So so there is, if you want to have a look at what it looks like, then you can use a tool called what to WASM, and then you can add parameter /v. Then you will get this listing, so you can have a look at what it looks like. But as you can see here, we don't really want to write WebAssembly by hand, because this is very tedious work here. So instead, what we would like to do is we would like to use a high-level language. But let's say here that we have this WebAssembly. So how do we use it? So we can create here a simple web page. And in this web page, we are loading our WebAssembly package by using fetch. And then we read the response into an array buffer. And then we can use here, since this is a web standard, we can just call WebAssembly.instantiate with this bytes array that we just read in. And then after that, we can just do this mathematical operation here. We can assign it to a parameter here that we call add2. So we just do results.instant and then .export, and then the function name that we define in our WebAssembly. And then we can just add two numbers here and alert it out on the console. So then we would have something like this. So we added two numbers, and then we got four out of it. So another tool that can be interesting to know about is something called the WASM Code Explorer. So let's say that you have a WebAssembly in binary code format. Then what you can do with the WebAssembly Code Explorer is you can upload your WebAssembly, and then you can see the textual representation of that WebAssembly. So this is what we've done here. So we took our binary WebAssembly, and then we uploaded it into WASM Code Explorer, and then we got this result back. And you can see that that's very similar to the function that we actually wrote from the start. But as I mentioned here, we don't really want to write it by hand. So instead, we would like to use a language here. So one of the high-level languages that are commonly used with WebAssembly is Rust. So Rust comes from Mozilla. It's a system programming language. It has a syntax similar to C or C++. It's a strongly typed language, and it compiles down to native code. And one of the design goals with Rust is actually that it should be memory safe guarantee. So you shouldn't have any dangling memory pointers or anything like that. So it doesn't have a garbage collector. So when you work with Rust, you need to understand the toolchain here. So the toolchain consists of three parts. The first is called the rustup, which is an installer for Rust. And then you have cargo, which is similar to npm. So cargo is the Rust package manager. So what you do is you make packages, and then you can upload these packages to crates.io, which is the package registry for Rust. And an example here of Rust program, we define a main function, and we print out hello world, and then we can use Rust compile on our Rust file, and then on the Windows system, it will generate an exe file, and it will print out this on the console. But what you can also use is you can use a tool called cargo. So if you run cargo new hello world, it will create this application for you. So it will create a binary application, a hello world project, and which consists of a main Rust file, and then you can write the print into your main function. And then if you run cargo.run, it will compile this, and then it will run the resulting exe file. And we also have something called a TOML file. So the TOML file is a package definition. So as a bare minimum, you need to provide a name for your package and the version number and also the authors. And if you have any external dependencies, you should define them also in the TOML file. So Rust is, since it's a high-level language, we have a lot more ways to express ourselves. So we have some primitive types, and we also have some primitive constructs that we can make use of. So now I'm going to show you how can we actually compile a Rust program down to WASM. So the first thing we do is we install this Rust toolchain, which was rustup, cargo, and Rust compile. And then we need to add a compiler target, which is called the WASM32 unknown target. So when we do that, then we can use a compiler to compile down Rust to WebAssembly. And then we also need to install a tool called WASM bindgen. So this will generate bindings to and from your JavaScript application so that it can call down to your WebAssembly. So this is again an example here, so that you can see that it's very similar here. We have the TOML file with a package definition, and also here you see that we have some dependencies on this WASM bindgen, which is, I call it as a glue file because this is the glue between your application and the WebAssembly. And here's the main Rust file. So in this, we define here that we're using an external crate, which is this WASM bindgen. And then we can use also external functions. So for example, here we are using the JavaScript standard alert function. And then we define our own function here, which we call greet, and it takes an input, a string, and then it uses the JavaScript alert function in order to print this out. Then if we want to package this, we can use a command called wasmpack init, and then it will make a package folder for us, which contains these 4 different files that you can see. And then we can just change into this directory, and then we can just do npm publish package as a regular npm package. And then we can see here that we got the hello wasp silver npm package uploaded to npm. But let's have a look into these 4 different files here so we can see a little bit more what is inside of them. So the first file here is a TypeScript file. And this is the definition of what are the different functions inside our WebAssembly that we can call from an outside function. So in this example, it's the greet function. And then you have this glue file that I was talking about. So that's a JavaScript file. So in this JavaScript file, we're trying to pass a string down to WebAssembly, and then we try to return wasp.greet, which is this WebAssembly function that we defined. And then we have this package.json file. And then what we can do if we want to use this package, we can define a regular webpack config file where we have an entry and index.js file. And then we can define also package.json where we have a dependency on our hello wasp silver that we just created. And then we can create an index HTML file where we reference this index.js file. And then we can load, and this is a little bit important that we need to load it asynchronously in order for this to work. So we can import our hello wasp silver, and then we can run the js.greet function in order to print this thing out. And then we get it out on our local host here. So this was a quite simple example here, but I can show you one little bit more advanced example, which is the game of life. So the game of life is sort of a standard application here. It's a simulation where you have like a game board with squares, and then you have different cells. And then there are some rules to this simulation. So if you have a live cell with fewer than 2 live neighbors, it will die because of underpopulation. And if you have a live cell with 2 or 3 live neighbors, it will live on to the next generation. And any live cell with more than 3 live neighbors will die as of overpopulation. And if you have a dead cell with exactly 3 live neighbors, it will become a live cell through reproduction. So then if we run this, one moment. Yeah, so if we run this simulation, you can see here that then we've added an event handler here so that we can pause this simulation. So now we're pausing, and then we go in and we edit the simulation. We add some more cells here. So then we're changing some parts of the simulation. So let's have a look at how this is done. So this is similar to the previous example. We have this TOML file where we define our packages, and we define that we need to have this wasp bindgen. Then this is our actual Rust file where we define this game plan that we call universe. So we define the width and height. So it should be 64 cells in the width and the height. And then we define some getters and setters for the width and the height. And we also define a toggle cell function that we used when we pushed the pause button. Then we could toggle the different cells on the game board. And again, we also have this TypeScript file with the different functions that we as an external application can call. And then we have our glue file here that you see, for example, in the toggle cell function, we're trying to call this return wasm.universe.togglecell and so on. So this is the way that you communicate from your calling application down to your web assembly. Then in order to use this, we can create an index.html page, and we have a bootstrap JS file, and then we're actually loading this thing here. So here we can import this universe that we had defined. And for example, we can run this universe.togglecell here that I've defined here in red. So one of the things that I started out with was that what WebAssembly is trying to achieve here is that we will have a good performance here. So this is some examples in 3 different browsers between JavaScript and WebAssembly in Chrome, Firefox, and in Safari. So what we can see here immediately is one is that WebAssembly is a lot faster than the JavaScript. But the other thing, which is maybe even more important, that WebAssembly is much more stable than what JavaScript is in terms of performance. So you can see that the deviation, these red dots in the box plot, they have a much larger spread for JavaScript than what it has for WebAssembly. So that means that you can, if you use WebAssembly, you can actually trust that you will get a specified performance. Whereas if you use JavaScript, the spread will be much bigger than for WebAssembly. And we should also take into account that JavaScript has been around for a lot longer time than WebAssembly. So we've had much more time to optimize our JavaScript engines than what we've had for optimizing WebAssembly. So some example here from the real world is digital signal processing library. So this is a classical example for when you should use WebAssembly. That's when you have an application that you have maybe in C or C++, and then you want to expose it so that you can use it on the web. So that's what these guys have done here. So then they made an application so that you can, in real time, you can apply different types of filters, both on video and on photo through WebAssembly. So the good thing here is also that, you have all the logic, you already have that, so you don't have to rewrite your application in order to get it out on the web. You only need to write, some glue files in WebAssembly in order to achieve this. And you also, of course, you need to compile it also, your application down to WebAssembly. And another example here is from AutoCAD. So AutoCAD, they have a lot of different types of drawings, and what they did here was that they wanted to keep, their legacy code so that their developers could continue working with it. But then at the same time, they wanted to use WebAssembly so that they could get these drawings out on the web. Because previous to that, you had to install a desktop application in order to view your drawings. So this is, I think, is an interesting architecture here. So first you have a layer on top, which can be any type of front-end layer like React or Vue. And then after that, you have a WebAssembly layer, which calls down to your legacy code here in C or C++. So I think this is also a good example here of separation of concern. Then some future plans here for WebAssembly. So as you saw here, we always needed to use this glue file here in order to call web to and from WebAssembly. But what they would like to do is they would like us to be able to call directly into the DOM or call directly to a web API, for example. And then you also maybe saw that we were loading WebAssembly asynchronously, but they want us to be able to just import WebAssembly just as any other type of package in JavaScript, and also support more languages. But you can also use something called serverless WebAssembly. So WebAssembly is not only for the browser. So the different providers, like for example, Cloudflare and Fastly, they support WebAssembly on the server. So what this will give us is faster launch time, and also you don't need to rewrite anything to JavaScript, and also some more lightweight applications. So here's an example here. So the blue box is a data processing code, and the green is the the main front-end logic. So we have some different ways that we can go about. Either we can run our data processing completely on the backend, or as in example one, or we can use some client-side JavaScript. So we run everything here on the front end, or you can use client-side WebAssembly, where you use WebAssembly on the front end, or you can use serverless. So there you are running WebAssembly on the server as a serverless function, and it serves your front-end logic. And then also for the future, they're also thinking about something called the WebAssembly system interface. So one of the things that we can't do, we can't call down to to the file structure or anything like that. So WebAssembly is running in the same security restrictions as JavaScript. But one of the things that they're thinking about is that maybe we could use like a middleman in between the WebAssembly and your operating system, so that WebAssembly actually could access your hard drive and the content that you have. So this is how they envision it, that WebAssembly will call an intermediate, and then the intermediate will pass on the files to the file system. I'm going to give you some examples of other frameworks that are also using WebAssembly. So one of them is called Pyodide. So what Pyodide is, it brings the Python runtime to the browser. So Python is used in data science and machine learning, but now with Pyodide, you can do all of this in your browser through WebAssembly. So you can use your regular libraries like NumPy and Pandas in the browser. Then we also have something called assembly script. So with assembly script, you will compile a subset of TypeScript into WebAssembly, and then you can just use it. So for example, over here you can see that we need to define if it should be an unsigned 32-bit or an integer 32-bit, for example here. But one of the important things with assembly script here is that then you're also responsible for memory allocation. So if you do something with some memory, you need to free it up afterwards. And we also have something called Blazor, which is a Microsoft framework. So the idea here with Blazor is that you can build your whole web application using C#. So you can either have Blazor running completely on the server, or you can run it through WebAssembly. So then they have compiled a special version of the .NET framework to WebAssembly so that you can use it in your browser. But one of the things here that we need to think about, isn't this just the new old? Haven't we seen this all before? So in the past, we've had, for example, ActiveX objects, and we have had Flash, and we also had Silverlight. But if we compare this to WebAssembly, one of the differences is that WebAssembly is a web standard. So that means that you can use it straight away. It's not a proprietary technology. It is supported by all the major web browsers. So I think this is a really positive thing for WebAssembly. So so to conclude here, what is the conclusions? Should we go WebAssembly, all the things? So when I started looking into WebAssembly like a year ago or something, then there were lots of articles which said that JavaScript is dead, that WebAssembly will take over everything. But I don't think that is actually the case. I think that WebAssembly is just one more tool in your toolbox, which has its own specific usage areas. Like, for example, when you have a legacy application and you want to put it out on the web, is for example one, or if you have something which requires lots of calculations, like a game engine, for example, or some mathematical operations, that's a good use case for WebAssembly. But we're still quite early on into the WebAssembly journey here. So there's a lot of tooling that I think needs to be improved in order for this to be something that every web developer can and would like to use. So with that, I would like to finish this with giving you some references. So you will also get this as a printout, as a PDF file, so you can have a look at this a little bit more at your own pace here. So I would like to thank all of you for watching here. And if you want to reach me, you can either reach me on Twitter or you can reach me on my email address. So thank you so much for listening into this.
Thank you, Håkan, for sharing your knowledge. It was very interesting, and I don't see any questions. But yeah, as Håkan said, you can contact him privately. You will receive an email with all